Hello everyone, today my topic is van der Waals equation. So, van der Waals equation is a description and calculation for real gas. When we mention real gas, you must be familiar with ideal gas. So, in part 1, I want to take you guys to review the difference between ideal gas and real gas. So, ideal gas formula is PV equal to nRT, and P is pressure, V is volume, N is moles of gas, R is the constant, which equals to 8.314 when you use unit Pascal, volume liter, mole, and Kelvin. In real gas, there are new elements like A and B. And in ideal gas, the molar volume is larger than real gas. In ideal gas law, the molecular size and intermolecular force is ignored. However, in real gas, these two elements are important and they are considered. So in real gas, at low pressure and high temperature, the gas is close to ideal gas. And in real gas, at moderate pressure, the more compressible V decrease is more than expected increased pressure, and high pressure, less compressible V decrease is less than expected increased pressure. So, in ideal gas, it without A and B in like the real gas law equation. A is a constant related to the intermolecular force. B is a constant related to the molecule size. So, when I mention A and B, let's move on to the part 2. So today my deep level topic is take you guys to see my process of the researching about A and B. So I said intermolecular force is considered in real gas law and it related to A. So what is intermolecular force? The two molecules, their distance at d1 and F1 and F2 is their intermolecular force. And on the right, d2 is this molecule's distance, and F3, F4 is their attraction. So F1, F2 is bigger than F3, F4 because this has has longer distance. So which means attraction is related to 1 divided distance. So, what ideal gas law considered is a gas molecule in a closed container. There are numerous molecules around this molecule, but I only draw one. So, the molecules in the center is pulled by F1 and F2. However, in this direction, the force is cancelled because F1 and F2 has different directions. So, just like F3 and 4. What it means? It means the net force on the molecule is equal to 0. But what ideal gas law doesn't consider, but van der Waals consider, is the real gas, just like the gas molecules stick to the wall of the container. The F1 and the F3 force is cancelled, but no force can cancel with F2. So the net force on the molecule is unbalanced. Since F2 wants to pull the molecule to the left, you can say F2 is pull the molecule to the left. The pressure for the molecule exerted on the container's wall decrease, and we call this reducing pressure by Pj. And we can get P ideal is equal to P original plus Pj. So we get this formula, P plus Pj multiplies V. Subtract B is equal to RT. And let's talk more about Pg. There's a molecule N here. There are several molecules around A, and if there are more molecules around A and more dense molecules surrounding the molecules, the attraction force on the A is equal to K1 K1 is density and N is number. If K1 the density or n number is increasing, the attraction force is increasing. Just like the force, the pressure exerted on container is also equal to K2m. K2 is density and n is number. So it's clear that Pj multiplies F is related to K1 K2 m squared, which multiplies these two formulas together and related to n squared. And n squared is related to n squared divides v squared. V is volume. Because n, I said before, is a number of molecules. It's a constant in experiments. So which we can replace by 1 and n. So we can get this formula. This formula is corresponding to what I said in the van der Waals equation. Because I used only one molecules in the diagram, so n is equal to 1, so I don't write n squared here. You can see it's also corresponding to the P ideal. So that's a summary of process by where A comes from. A is a constant related to intermolecular force. Intermolecular force, ideal gas law, ignored. So let's talk about the volume, about B. Ideal gas law ignores the size of gas molecules. So which means the collision of many gas molecules, their collision space is decreasing. So we get V ideal is equal to V original minus B. Let's talk more about B. You guys know, I just know that volume is related to B. So I will take an example here. There are two gas molecules here, and both of their radius is r, and their collision radius. What is collision radius? Think about it. You just rotate the two circles about 360 degrees, and you will find that the way it rotating forms a new circle, and the new circle's radius is 2r. And from mathematical equations, we can get the volume single molecule is 4 divides 3 pi r in an r3 power, and the volume of collision space is 4 divides 3 pi 2r 3 power. Because what I draw is circle, but in the world, a gas molecule is sphere, so I use the sphere volume here. So from these two molecules, we get V collision is equal to 8 V molecule. And another example is also a closed container, and the space for the first molecule, available space for the first molecule is equal to V container, because the first molecule can choose any space to exist in the container. However, the second molecule has only available space V container substrate V collision. You may confused about this. Why not V container minus V molecule? So this is a diagram from geometric structures of the circles and the spheres. You can see that when many circles are close together, there were many blanks among them. These blanks I draw in the black color. These blanks take up the container space, but they cannot used as circles available space, because gas molecules are not fixed. They never stops the motion. So when a new molecule wants to enter in the closed container, it must consider the collision with other molecules. So the second molecule available space is V container minus V collision. The third is V container minus 2 collision because it needs to consider with other. It needs to consider the collision with other two. So the nth molecule is V container minus n subtract 1 V collision. So I want to get the average space available for the V container. We just need to add 1, 2, 3 to n together, add their available space together, and we divide the number of molecules. So we get the average space available for each molecule. So that's the result. V available bar is equal to a V container minus n V collision divide 2, because we know that V collision is equal to 8 V molecule. We replace it with V container minus 4nV molecule. And I want to give the 4nV molecule to give it to B. And we know that nV molecule is all molecules volume, so B is equal to 4 multiplies total molecules volume. So that's a summary where B comes from. The B is a constant related to the volume of molecules. So by combining the result with A and B, we get the van der Waals equations. So after talk about A and B, I want to give you guys a sample question. Use the van der Waals equation to calculate the pressure exerted by confined to a volume of 2L at 273 K for CO2. A is equal to 6.34 bar, B is equal to 0.05 air mole, and talk about which is the main cause of departure from ideal gas. There are two little questions here. So the first question is easy. You just need to put this data into the van der Waals equations, and we can get P. P is equal to 10.1 bar. The second question, how to do the second question? We can suppose it's in the ideal gas situation. The Cl2 is in ideal gas situation, so we don't use A and B in the question. We just use PV equal to nRT, and we get P is equal to 11.3 bar. And to compare in the intermolecular force A and volume influence B on Cl2 pressure, we include only B in the van der Waals equation, which means we put all elements and B except A in the van der Waals equations, and we get the pressure is equal to 11.7 bar, which means the 11.7 bar, it has only 0.4 difference with ideal gas equation, but when we both conclude A and B, the difference between ideal gas and A and B considered is 1.2. So which means A plays a more important role in the departure of from the ideal gas of the Cl2. So A is closely related to intermolecular force, which means intermolecular force is the main cause for departure from real gas, from ideal gas. So that's all for my today's tutorial. I hope you guys can understand what I said about A and B. Thank you.